Hi, sorry, hi. I'm Wei-Che from National Taiwan University, and my advisor is Professor Zhang Jie. And today I'm pleasure to share my topic about semi-automated pedestrian verandas quality assessments. And this is my outline today. So in Taiwan, actually, we have a rainy climate. So most of the buildings are designed with the verandas. So, but with the urban development, there are more used for like the vendor seating, or even you can see the motorcycle are parking on the sidewalks. So it creates significant obstacles for pedestrian and accessible environment. And in Taiwan, the current assessment regulations, we actually focus more on walkabilities. And in the category of walkabilities, we have much more, a higher weight in net width. But there are also some more important indicators like the comfort perceptions and even the continuity. So because current assessment they require on-site manual measurement, so it consumes a lot of time and labor. So the research aims to explore the advantage by applying the computer vision analysis to estimate the width estimation. And also it aims to evaluate the accessibility of the veranda spaces for the pedestrian and maybe some individuals with disabilities. So to achieve our goal, we have to collect three types of data. The first one is on-site measurement. This is for our verification. And the footage of the verandas, this is the materials that we're going to do the width estimation. And the main logic happens in the geometric calculation, which will be mentioned later. And the third position angles, we will collect yaw, roll, and pitch angles. And this data to classify some pattern, what it means in our evaluation. So our experiment tools are so simple. We just have the gyroscope to record the tilt angles and the sport camera to record the footage. And we put it on a wheelchair and we collect the data near the Wei-Che MRT station in Taipei City. Okay, so let's talk about the geometric calculation. So let's see in this picture. This is a 2D image. Does the A equals to B? No, of course not. It's shorter than B, right? But in reality, let's think about a railway. Two parallel lines. There always has the same width between two parallel lines. So in order to estimate something that is has the same width, but it's not in the 2D image, so we have to make A equals to B in 2D, right? So how to achieve this to scale A or B to be the same width, right? So let's recall some high school math. That's about the intersection theorem. So between parallel lines, there's triangles. If no matter what shapes or where it is, it always has the relationships like OA prime over OA equals to OB prime over OB equals to A prime B prime over OB. So this is the very simple math principle of this estimation. So in order, if we see some parallel lines in our picture, and if we obtain the vanishing point to create a triangle of our image, we can find not only A and B, we can even push further to the whole width of the veranda pathways. So we can even get C. So let's explain a little bit further. Okay, so actually in computer, you can get every position of the pixel in computer, right, on an image. But what we don't know is that the real length of, let's say, A prime, B prime is the wanted line that we want to measure. So let's assume that A prime, B prime is equals to W prime. So AB is the non-width that we do on-site measurement. to get the real length. And then the pixel length of AB and A prime, B prime can be obtained in the computer. It's just, you can just get maybe the coordinates X and Y to get the length. So let's define S is actually how long is one pixel represent to one represent real length. So let's say S equals to W divided by P. So the second equation means that we have to, as we mentioned before, we have to make A equals to B into this situation. So we have to make W prime equals to W. So that equals to S times P. So what's the relationship between P and P prime? That we can use the intersection theorem, as we mentioned before. So we can get the P equals to OD over OC times P prime. So combining the three equations, we can finally get W prime equals to that bunch of equations again. So this is the equations that we're going to use in our width estimation. And as for the pattern classification, according to American with Disabilities X, they give us some factors that is important for the sidewalk. For example, sidewalk corridor and grades and cross slope and sidewalk surface. And we want to, and we also come up with our desired and want to focus on the continuity. So in these factors, we use our data accordingly to try to evaluate the condition of the verandas. So what kind of pattern that will be probably shown in the data? We have to come up with some common patterns. The first one is like the corner. Yaw is something like when you're standing there and you turn left or turn right. Okay, so corner means like when we go through a corner, we will be turning right or left in a short time. So the angle will like drop or rise in a short time, right? And if we encounter some obstacles that is passable, then we might try to get right and left go through it, or left or right go through it. So the pattern will show like it goes up and down and up, or up, down, up in a very short time. And as for the third one, if we encounter obstacles that is not also passable, then we might try to turn around and find some ways. So we might try to turn like 180 degrees around and then find some ways, and then we turn back again, then we can keep going. Okay, so the last one is the most simplest one. The simplest one is just stop, just standing there, do nothing. Okay, so pitch and roll, they are relatively simple. For pitch, it's just like you're going through a slope that is going up or going down. So it's like an uphill or downhill. And the roll is means like you're rolling left or right. So it also shows like it's increasing or decreasing. Okay, so that shows some small results of our estimations. So we have took some of the pictures in it, and let's see this one and this one. They are between the same parallel lines, and our method successfully estimate that they are almost the same, about 45 centimeters. And for the on-site measurement, we also do the on-site measurement to verify our estimation, and it's all within like 2% of the error. And as for the longer distance, the whole path width of the verandas, we on-site measure about like 340.2 centimeters, and the estimation is about 334.14 centimeters. It's also within 2% of error. And we try another scene. This is different scene, and we try another scenes to see that if our method applied to other situation. So we can see that our estimation is also within like 4 to 5%. And as for the pattern classification, in our whole section, we can see that this is the yield type data. We can also see there's 4 corners. and it is the same as the reality situation. And we also encounter 3 path change in section 2 and section 4. And the pitch data, we define that a steep hill, which is above 10-degree slope, and we encountered 19 steep hill during our whole experiment. And the road data main side, if we encounter a larger road which is more than 5 degrees, then we say this is a larger road. And we encounter a larger road in section 4, which is relatively bumpy in our the whole section. And we also compare our time efficiency with our method and the on-site measurement. And we took a single point and about 3 points to compare the situation. And in the on-site measurement, we do the single point, we took about 50 seconds to measure the width. And for the 3 points, we include the traffic time. It took about 5 minutes. And for our method, we took about only 8 seconds to estimate 1 single point, and about a minute to estimate 3 points. So it actually saved more than 80% of the time. So in conclusion, our width estimation can actually significantly reduce the time to save some time for the labor. And we also give the accurate enough results that is within 5% of error that can sufficiently give the cost-effective and a better results and a better approach in the future. And as for the pattern classification, it actually reflects the real condition of the verandas. And if we apply some limitations and standards to it, and we can actually filter out some of the data, and we can see that whether this veranda is smooth enough or is also have a good continuity. So overall, our method actually shows a good potential to provide it for our future assessment. Okay, in the future, we're going to use our results to establish a storage system. So yes, and now we're still doing this part. Okay, so this is my reference. Thank you.